Welcome back to the first video about the details of RS-485 communication. In the second and last video about the basics of RS-485 communication, we established a serial link via 10 meters of Cat3 twisted pair cable between two Arduinos using two SN75176B transceivers. Card here, link in the description. However, at the end of that video I told you that the code for our Arduinos contains a fatal flaw and we'll have to fix that. In addition, we just have one master and one slave, but RS-485 is a bus, so we want our master to be able to talk to at least two different slaves. Both we will do in this video. Enjoy! Let's dive right in and explore that fatal flaw in the code we've created in the previous video. I have here exactly the same setup as before, so here's my master, here's my slave, and the slave is powered by that USB bank. And if I type in here an E, I get back an echoed E. So the master sends over the E to the slave and the E responds by sending back the E to our master. However, what happens if I switch off the slave and then I type in a C? Well, obviously nothing, because our slave is dead. Now if I switch the slave on again and try that C again, nothing, absolutely nothing. Dead as a dodo, the whole thing. I really have to reset the master, and now I should be able to send a C again. Yeah, working again. Let's have a look at the oscilloscope. The oscilloscope is on single capture and I'm switching off the slave again and I try an H. That looks funny. Let's have a closer look. It seems like that our RS-485 bus entered a continued undefined state, meaning neither the master nor the slave is driving the bus anymore. And if I scroll a little bit over here, yeah, I didn't capture everything, but enough. Here the master is sending the byte over to the slave. About here the slave stops listening to the bus. And here at that point the master is releasing the bus. And then the bus stays dead forever. If we have a look at the code of the master, that behavior is easy to explain. And I went over that code in the previous video line by line, so I only point out here the important stuff. As soon as we receive a byte from the serial monitor, we write it to our RS-485 bus. We release the bus, start listening to the bus, and then we wait for the reply from the slave. And, well, we wait forever. That is, we are in desperate need of a timeout. If we have another look at the protocol diagram we've created in the previous video, you notice that we have defined a t-cent max. That is the maximum time in which the slave has to respond to a request from the master. However, t-cent max is nowhere to be found in the code of the master. We have t-def, t-release, t-grab and t-listen, but no t-cent max. Now, t-cent max is not directly our timeout. We have also to consider that the transmission takes some time, then the processing in the master takes some time, and then we can also add a little tolerance here. So we have a t-cent max plus something which depends on the processing speed and the length of the transmission. And here's a new code for our master implementing that timeout. I've added a constant unsigned long t timeout in microseconds, and it turned out that 2 times a t step in microsecond, so the base duration of our protocol steps, is a suitable value. When we look later at the oscilloscope, you will see why. No real changes to the setup, but for the fact that I swapped the pin mode and digital write statements for the data enable pin and read disable pin, bringing them into the more conventional order. Turned out that the little trick I introduced in the basics video doesn't really work that well. And in addition, that little low spike we get on the read disable line and the data enable line doesn't really hurt. And now for the main course in the loop. I will only point out the changes. I've added here a new local variable unsigned long timeout microseconds, and I'm now, after we get a byte from the serial monitor, echo that byte back locally. That's just to make things more readable on the serial monitor. I also optimized here some timings and I reformatted the commands. Nothing to write home about. The interesting part starts after we write a load to our read disable pin, enabling our receiver and listen to the slave. First, I calculate the timeout in microseconds as micros plus our t timeout microsecond constant. Then I go into a loop which I only exit if I either receive something from the slave or our timeout occurred. Then I do immediately a digital write to the read disable pin of high. So we go deaf to the bus, stop listening to the slave, and then I check if we indeed received a byte from the slave. If that's the case, I write that byte out to the serial monitor. Otherwise, I write a tilde to the serial monitor indicating that we had a timeout. In that block here, I only optimized some timings and also reformatted the comments. Finally, I write a new line, ASCII 10, to the serial monitor. That's just for readability purposes. Let's have a look at the serial monitor if that really works as intended. Again, here's my master, here's my slave, and here's the power bank powering the slave. And I type in echo and we get, the first letter is the local echo, and the second letters are the echoes from our slave. So echo. And now I switch the slave off, and again I type echo and we get, ECHO, tilde, 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 tilde. Timeouts. Switching the slave on again, and echo again, and echo. Very good. Let's have a look at a normal transmission on the scope now. And I had to switch off some lights because of the reflections on the scope. E. There it is. Let's first scroll over to the start. Here's the byte the master is transmitting on the differential line over to the slave. And I also probed the master's transmitter enable line and the master's receiver disable line. So around here, our slave stops listening, and then our master is disabling its transceiver. So the differential line, we saw that before, goes into an undefined state. Then around here, the slave is taking control of the bus, enabling its transmitter. And here we see our master is enabling its receiver. And then the byte is echoed back over the transmission line from the slave. After which the master is disabling its receiver again, and the slave is releasing the bus, disabling its transmitter. And after a while, our master is taking control of the bus again, enabling its transmitter again. Now let's do the same with the slave turned off. And yeah, we have here a timeout. Scrolling to the start again. Here's, like last time, the byte transmitted by the master, but of course there is no slave receiving it. The master anyway disables its transmitter and the bus goes into an undefined state, and it stays in that undefined state because our slave is dead. After a while, our master enables its receiver and it receives absolutely nothing. After the timeout occurred, the master disables its receiver, and in the next step, the master enables its transmitter again, and our bus is back in a defined state. Great! Now that we've established a more robust communication between our master and our slave by using a timeout, we might want to talk to more than one slave. I mean, it's a bus after all. So, let's just do that. Here's a new setup. As before, the bus goes via 10 meters of twisted pair cable to our first slave, but then continues via another 10 meters of twisted pair cable to our second slave. So we have now that typical RS-485 bidirectional half-duplex bus setup with a single master and several slaves that I've shown you in the basics video. Card here, link in the description. Please note again that the bus is only to be terminated at each end. In our new setup, the master is still connected to one end of the bus, but now the other end of the bus ends at our new second slave, while our old first slave is somewhere in the middle. Consequently, I moved the termination resistor from the first slave to the second slave. And of course, we keep that termination resistor here on the master. Now let's address the elephant in the room. We need a mechanism so that the master can address the slave it wants to talk to. In most protocols that use RS-485 as their physical layer, the master transmits before the payload, in our case the byte to be echoed by a slave, the address of the slave it wants to talk to. So our master message consists of 2 bytes, the address of the slave and the byte to be echoed. As an address, we will use ASCII characters, so 1 for our first slave and 2 for our second slave. The byte to be echoed will be binary as before. We can represent that message in our code as a byte array of the size 2. So message 0 would contain the address and message 1 the byte to be echoed. The message from the slave has exactly the same format, so first the slave's address and then the echoed byte. Please note that we will not simply echo back that message here, but we will explicitly write the slave's address into the first byte to prove that that message comes really from the slave we have addressed. That leaves us with the question how the slave that is not addressed should behave. The answer is fortunately quite simple. The not addressed slave will, like the addressed slave, disable its receiver within tdef after receiving the message from the master. And like the addressed slave, it will keep its receiver disabled until after the master has taken control back of the bus. Let's call the time where the not addressed slave has disabled its receiver T standby. And of course, the not addressed slave never enables its transmitter. T standby should be chosen so that the addressed slave and the not addressed slave disable and enable again their receivers at the same points in time. One more hardware tidbit before we have a look at the code. Because I want to use the same sketch for both slaves, I will use the digital 21 pin to set the slave address. If the pin is pulled to ground, it's slave 1. If the pin is floating, it's slave 2. And here you can see how the digital 21 pin of slave 1 is pulled to ground, while on slave 2 it's floating. Let's go over the code now. Master first. I twiddled throughout with the timings. For example, a T timeout is now 3 T steps instead of 2 because we are transmitting one more byte, which takes an additional 10 microseconds, so 1 T step. Setup remained unchanged. In the loop, I've added as a local variable that 2-byte array message. Remember, message 0 will contain the address and message 1 the byte to be echoed. Then I'll wait until I get at least 2 bytes available from the serial monitor, otherwise I exit the loop. If 2 bytes are available, I read them into my message and then I immediately write the message back to the serial monitor, just a local echo of the message. Then I write the 2 bytes now to the bus and the rest is unchanged. Up to the point where we wait for either a timeout or a message to arrive, and of course we check here no longer for a single byte to arrive, but at least 2 bytes. The next line is also unchanged, and here where we handle the timeouts, I check if actually 2 bytes are available on the bus. If they are available, I read them into the message and then I write the message to the serial monitor. Otherwise, I'm now outputting 2 tilde because we're missing 2 bytes in the timeout to the serial monitor. And the rest again is unchanged. But for the fact I just spotted that here I really had to turn down the delay to keep within our timings, because all this array stuff here and reading multiple bytes, it takes some time. So basically no longer a delay here. In the sketch of the slave, I have a new constant byte here, address pin, digital 21. Remember, if that pin is low, we have slave address 1. If it's high, slave address 2. I also have here now a global variable address. In the setup, I added a section to determine the slave's address. So I set the pin mode of our address pin to input pull up. So when the pin is floating, we will read high. Then I do a digital read on the address pin, and if it's low, I assign address a 1, otherwise a 2. That's it. In the loop, I added, like in the master, a local variable message. And analog to the master, I'm checking now if at least 2 bytes are available on the bus, otherwise I exit the loop. The step 1, slave goes deaf on the bus with int-deaf, moved up here because of timing reasons. All that handling of 2 bytes and the other processing takes too long, and we want to go immediately deaf to the bus, disabling the receiver as soon as we received 2 bytes. Then I read the bytes into my message, and then things get interesting. First we check if the master has really addressed that slave. If that's the case, we do our protocol dance for an addressed slave, which is unchanged. And then, just to prove that's really the addressed slave that's answering, I'm explicitly writing here the address of our slave into message 0. Then, instead of just echoing back 1 byte, I'm writing back the whole message to the bus. And the rest again is unchanged. If our slave has not been addressed, then I just wait 12 t steps. That's about the time all the above stuff needs to be processed. And only after that I enable our receiver again by writing low to our read disable pin, like we discussed in the protocol for the not addressed slave. And that's it. Now, let's enjoy the fruits of our labor on the serial monitor. Let's start with 1E. Perfect. So the master sent 1E onto the bus and the first slave responded with 1E back to the master. Let's try 2C. Works also. Master sends 2C onto the bus and the second slave replies back 2C. And 1H, 2O. And we have again our echo. But what happens if I now address with 3X a non-existing slave? Of course, we get a timeout. That mechanism is still working. And also if I switch off the first slave and say 1Y, no reply. Sorry, joking. But let's switch that slave on again and capture something on the oscilloscope. I'm probing now on the oscilloscope the receiver disable lines from top to bottom, the master, the first slave and the second slave. And at the very bottom of the oscilloscope we see the B line of our differential bus, so the line that carries the inverted signal. And now let's do again 1E and perfect. That is perfect. Let's have a closer look. We start with the master transferring the message on the bus, which is received by both the first slave and the second slave, after which both disable their receivers. Then our usual protocol dance starts, transferring bus control from the master to the first slave. After that's finished, the master is enabling its receiver and the first slave is sending back the message on the bus. As soon as the master has received the reply, it disables its receiver. And the usual protocol dance starts again, transferring control back from slave 1 to the master. After which both slaves enable their receivers again. And yes, I could have optimized the timing here at the end a bit more. That's it for today. We have now, thanks to the timeout in the master, a robust communication. And we have a real bus, that is, we can now address multiple slaves. But what if I told you that our little setup still has a possible source for errors? And that we could eliminate that error source by the use of 2 resistors and at the same time simplify our protocol enormously. And that's exactly what we will do in the next video. Till then, bye!